fixed, 3rd of March. So will it be all right if I make quiz 2 on Monday, 14th?
Yes, sir.
Students, you don't have any problem with shifting and all that, okay? In the hostel, I think many boys are coming. So because that was shown by the second year students, I made arrangement, postponed it. But quiz 3 will be 3rd of March, that is fixed. Okay?
Sir, class timings?
In the class itself. Monday in the class time, 4:30 to 5:30. Is it okay now? So you will be free from quiz number 2, and in the next class I will start module number 3. So up to Friday, I am going to talk about module 2 only. For your convenience, all doubts etc. I will be bringing. Today I will be completing the discussion on clippers that I have already done. Clamper also I will complete today, and Friday will be the revision of all this. Okay, so Monday will be your quiz 2 test. Fine now, all other centers, I think they are there. They should note down in the class timing itself, 4:30 to 5:30, quiz 2 exam will be conducted. In a similar manner, the way quiz 1 was done, it will be like that only. Fine, so I will take the presentation handler. I will go ahead with the discussion part. It's not coming to me, Professor Gupta. Handler is there, now it's coming. Oh, very slow, okay. Very slow. These 3 are the different types of inspection and the transmissions that we use. So you can see my screen and you can see my lines also. Is it okay now? Fine. I have done clippers using diode. Clippers 2 ways. Top is clipped, removed, bottom is removed, or only one is removed, that is one. Another clipper says only few portion of the top is selected, few portion of the bottom is selected, and for that only battery remain the same. Sorry, battery polarity remain the same. Diode polarity, sorry, made a mistake. Diode polarity remains the same. Battery polarity is changed. Okay, so it becomes your selection of the peak, or you can say clipping and removal of the peak. That way it will be there. So clippers I have done with diodes. I think might be having this question in your mind. In the book also it is given clipper using transistor. Clipper using transistor. Here only some portion of bottom is clipped. Some portion of bottom.
Doesn't give any variations at the center. Profile is same as that.
Signal is clipped. Why? Because it is inverting amplifier. Transistor is inverting amplifier. So actually the top portion of the input signal that is not supposed to be there. but at the output is inverted, so top becomes the bottom. So some portion of the bottom of the signal that will be clipped. Signal is clipped. Okay. Circuit you also already know. I'll just drop for the sake of completeness. I take PNP for example. Here is my RC. Here is my VCC. NPN transistor I have taken. Let it go to ground. I put some resistance, cell biasing circuit. It's up to you. This is my base. Base is also biased. In whatever way you know, I will put it here in a simpler biasing circuit using the potential divider also. So this is supposed to work as a clipper. When it is not clipping, what is happening? This is my signal.
Similarly, for dipoles and other antennas also, we can scale down their size. So first,
what is the amplitude of this signal? Where is the zero for the input? At base it is applied. Where is the datum? Zero. Zero will be somewhere here.
Some reduction in gain value will occur.
Zero is somewhere here. And the difference between the negative peak and the zero, this is my zero ground. 0 volt. Between 0 and this difference will be equal to your V gamma. This portion voltage will be V gamma, cut-in voltage of the diode made by the base and the emitter. So this is a V gamma. So if it is above V gamma, only then it will be amplified. So that way DC shifting is done. If not done, if it goes below that, that portion will be cut. I don't say that will be a clipper because that is a part of your transistor characteristics. So clipper you have to design. Here there is nothing like any design. Okay. So here this is V gamma, and if V gamma is satisfied, it is above V gamma. Negative or bottom of the input signal is V gamma. Corresponding to that, what I am going to get, this is my signal. Suppose I am taking sine wave, I can take cosine also. This is my sine wave. What is going to be my output? Output will be, I take.
This size is also dependent on the substrate that we are using, because the relative conductivity of the substrate will play a major role.
Agreed now, okay. So output will be coming as the amplified version. So output will be something VI into A.
Length in the free space. But when we are designing it on a particular substrate, the actual wavelength will vary as per the free space wavelength.
It will do the same thing here through merging. So this is the amplifier output. Okay. If it is working as amplifier, this green is the output. Is the output. And this black is the input. Okay. The question comes in your mind, what happens to this portion? This portion, is it less than 0 or greater than 0? This will be greater than 0. It becomes less than 0, DC is absent only if you are putting a capacitor here. But for the case of clipping, you are not putting that capacitor. A question mark here. You put a capacitor, only then it will become a DC at 0. It will be shifting, DC will be blocked. It will become, this will become 0 in that case. If capacitor is put, it becomes 0. Otherwise not. It will be above the 0, 0 is somewhere here. Is that okay now? This you already know, it is inverted. Oh, sorry. No, sorry. I have done wrong. I have drawn wrongly. I think I'll take the other one. It is inverted, sorry.
Electrical size is almost
Okay. This is the one I have drawn. This was my input signal and let me see the output now. My output will be.
This is possible when the data size or the array size.
It will be inverted. So output inverted and amplified.
A huge number of small elements. And thus the number of elements can be increased as per our.
And so on. So this is my output. And this is my input. Input is fed at the base. Circuit I am drawing once again for the sake of your reference.
Zero interelement spacing arrays are also.
And this is your VCC.
Other words also feature. So the advantage of zero interelement spacing is that.
Okay. So remember your zero is somewhere here. If I make it your, it's gone. You cannot see that. Here. Okay, your zero is somewhere here because coupling capacitor I'm not considering while talking to this one. So your zero is somewhere here. In this case, your zero was somewhere here. In this case, the zero are somewhere here. Okay? Or you can put this has to be V gamma only. This has to be V gamma. Only then it will take amplification will take place and will come like that. At the output, for output, this is the zero. Zero I can put here as output. And this was the zero for input. Okay? So that's how it has come. Now question comes, when this becomes very high, this voltage, amplitude, V in, amplitude. Amplitude becomes very high. It becomes very high. So this one also will go very high, very low. This one will go very high. This one will go very low. Very low up to what point? It will not touch zero. Remember, it will be above zero only, unless blocking capacitor you use, coupling capacitor you use. It will be above that. So at that time, what happens? When Vi becomes very high collector current will flow. So this will become almost short circuit. I will call it VCES saturation. This becomes your positive. This becomes your negative. This is my VCES. And that will become constant. So what you are getting here is what we are getting here in the output is this is my zero. It comes like this, gets clipped over here. It goes like this because negative direction. We are not bothered. It comes like this, again goes like this. It comes like this. Yes, and this voltage is your VCES. And this is your zero. So it will be positive only. For PNP it is positive. For NPN it will be going in the negative direction. For NPN it will be going in this form. If this was my input, my output will be somewhere here.
Along with those side lobes, certain lobes will have a higher amplitude as
this one will be inverted in the same form. So this one will be somewhere here. And it will be your
particular from there, a particular one will slightly spike up. And that leads to what we call as the grading.
Here also it inverted in the similar way. NPN is not changing the polarity of my signal. So negative signal input becomes positive, positive becomes negative. These are V output.
This phenomena is like
What happens when the signal level increases? That means this becomes more negative, coming closer to your zero. This is becoming more negative. Okay? So here it was becoming positive, here it is becoming more and more negative. When it becomes very close to V gamma, okay? Not V gamma, what to do? VCES. So when it be VCES, this portion will be cut. So it is VCES will be negative voltage. VCES will be negative, sorry. It will be something like that. Okay, it's fine. It will be inverted, but shifting will be something like that. And this will be my VCES. It cuts here. It cuts here. It cuts here. This is my zero now. Zero for the output. Zero for the output, it is there, it is cutting like this. So this is my VCES. If I'm putting a coupling capacitor, it will be showing like DC blocked. And so that's what. So this VCES is the clipping. Two-way clipping, how to get that? I think that will be a design problem in some projects your teacher can give. Here you understand that portion by diode only. Okay, those problems you need not expect in your exams, etc. But this kind of things are there. When this VCES is coming, this is my collector.
Yes, but lots
this is my.
This is the latest one with zero interdelical spacing you get with it.
This is my IB. Let us say base current IB I am putting. Base current is changing according to that. If base current is changing like this, when the current becomes high, this voltage becomes your VBES. This voltage becomes VBES. Means that voltage which makes the transistor a saturated state. That voltage of VB at the base, which makes the transistor go to saturation. So this one, it is going above. Your V gamma is somewhere here. V gamma is somewhere here. That is your V gamma. It is smaller than VBS. So it becomes over more than VBS. For the NPN, it will be inverted. V gamma will be minus and something like that. VBES also will be minus, and that's what will be coming. So VBES is your something above V gamma. If it becomes like this difference makes the transistor into saturation, and at that point you will be getting your output as your output is amplified. I'm taking some red one here. Your output is coming as the amplified one, and at this point it will be cut. It will be coming at the amplified one. At this point it will be cut. So VB is becoming VBES. Okay, because your base current is increasing, you are going toward VBES. So this becomes my voltage, V out. Now question comes, if it becomes very small, if this voltage becomes very small, sorry, negative one, sorry, this one is here, a zero is here, this becomes very small, less than V gamma. So when this becomes less than V gamma, something like zero is here, so it becomes a negative, less than V gamma, much less than V gamma. At that time, what will happen? This output will be VCC. Once again, it will not be a clipper. I cannot say it is clipping at VCC. No, it is not a design related parameters. So VCC is a biasing related parameter. That VCC will be getting clipped because it becomes a cutoff. Cutoff means when the transistor here is cut off, no current is flowing through this. I am taking output at this point with respect to ground. So this VCC will come here because no current flows through this R. So that will be this VCC. So, but VCC I cannot say it is a clipper design parameter. Okay, but this one yes, VCES. This output it is clipping at this voltage when my input is exceeding that particular limit. At that particular limit, how do I design? By choosing this R1 and R2. R1 and R2 design will bias it at V gamma such that any fluctuation there makes it cut off and makes it saturation. If this one is much higher than V gamma, any small voltage will make it to saturation. That is something like a transistor clipper. People discuss even in the book. So if question is there, I can appreciate it. Okay, so VCC is not a design parameter. That will be the parameter for the transistor biasing. And here, at what level I want to clip, which particular signal level will appear at the output as a clipped one. Clipped one will be at VCES. Clipped one will be VCES. But some higher voltage will be clipped at VCES. Sometimes some lower voltage will be clipped at VCES because of this biasing of this R1 and R2, not of this RC. Okay, you can design. So you can say VCES output is clipped over there, but which portion, how many voltage of the input shape is clipped, that can be designed by R1 and R2, proper choice as to. Okay. So this is about your clipper circuit. Now I'll go to clamper.
This is shown just for 2 elements. And if we increase the number of elements,
yeah, clamper circuits are something like that. I'm just giving you the idea. Then I'll discuss that technique in that. Here is my source voltage Vs. I'm clamping it. Vs is a function of T. It can be a square wave, it can be sine wave, it can be anything. Here is my ground. So Vs is applied. I'm calling this as positive and this is negative. For sake of my reference, with respect to ground I'm making, so ground I'm taking as 0, negative I'm taking as 0. There will be a source resistance here. That will be your RS. There will be a capacitor here. Its value is C. And at the output, I put a diode. In forward bias, just see that. I put that in the forward bias. The signal will be clamped. Okay, I'm giving this value. This input VST will become VST minus VST maximum. So this minus, so it will be clamped to a negative voltage VST minus maximum VST, that is amplitude, sinusoidal signal is amplitude of that. If it is square wave, similarly, what is the maximum value? So VS square wave once again going in both the directions, plus and minus, remember. Then it will be your maximum amplitude for bidirectional case. Or bipolar you can say. Okay, bidirectional.
So next we see how
if VST is bidirectional, I'll take it as a VS maximum, it will be clamped to that. Okay, so that way, or you can say in general case VST
This is how the length varies. But when if we imagine
minus, this will not be Vs maximum, it will be your Vs maximum
this is how it varies, and it moves. We have
minus
receiver as well as the transmitter,
VDC.
and the total it comes to the power.
VDC is 0, it will be Vs maximum. If VDC is not 0, V maximum minus VDC. So VST minus Vs maximum minus VDC. That will be the output. Here is my output.
So that varies as to the power of 4. So that is one of the.
How does it come? I'm going to explain that. Okay. So it will be clamped to that because of that. So the C will be there. RS and C will control something, the shape, but it will not be that much significant. Because normally we take RS to be small and C to be large that way. So anyway, that is the thing. Okay, this is clamping circuit. Another clamping circuit comes here. Here is my RS. Here is my diode. And I put some kind of design load. I can put that load here. I can put a load here. That's not your next stage load. That is a part of the circuit itself. I'm putting a load parallel to the output. I'm putting here. This is a diode. This is my RS. This is my C. This I call it my R. This is my diode. This was my diode. And the diode, you can say it has got resistances RF and RR. So this will give you some of the numerical problems by which you are going to compute the output case. If RF is 0, RR is infinite, you are safe. It becomes ideal diode, and but R is here, remember, R is remaining here. That will be the one who will control the output. Here RF and RR both are there. Okay, so what will happen during the forward bias case? RF resistance is there, and this voltage or the output will be decreasing according to the time constant. What? C into RF. Will it be RF? No, RF plus RS. RS is also coming in series for capacitor to discharge. So capacitor discharges through RS plus RF. Okay? When the diode is reverse biased, RF is coming here. Okay? So capacitor will be charged, okay, according to RS plus RR. According to that voltage, your time constant, RS into RR, to that time constant, it will be charging. If RR is infinite, that charging will not take place at all. Okay, here this R is also coming. So what will happen? R parallel to RF in series with RS will be the charging case. Will be discharging case. Okay, initially capacitor is not charged. So the voltage comes here. After that, capacitor charges, you can say. Capacitor charges will become negative. Sorry. And when the negative voltage applies, diode becomes reverse bias. This becomes your RR. So RR parallel to R in series with RS. RR parallel to R will be approximately equal to R only. That can be neglected in limiting case. Otherwise, R and R both will be there in series with RS for the capacitor's discharging circuit. Charging takes place because whatever voltage apply, initially there is no charge that appears here. After that, the capacitor starts charging through the RS and this R parallel to RF. So it will be decreasing. If capacitor is charging, this voltage will start decreasing, say like this. like this, e to the power minus t by, here it will be your r dash into c. R dash will be what? Rs plus r parallel to rf. Okay, r dash is rs plus
certain antennas which specially we need for larger
r parallel to rf.
There the characterization is different, and in those cases the
okay, so by that it will be discharging, it will come up to this voltage. Sinusoidal is there, so it will not be, actually sinusoidal amplitude will be changing. This will be obvious for the square wave, but sinusoidally it will be changing, and that's all. So this capacitor charge will be taking place. This one will be subtracted from the your sinusoidal signal. That part. From the sinusoidal signal, that part it will be subtracted. Value e to the minus t by r dash c, that will be there. Anyway, I'm coming to the analysis of this and this. These two are the circuits based on which several numericals have been done. Here it will be your sinusoidal input, or it can be a square wave. There can be a zero here. So you can be a V maximum. This is your V min. It can be positive, negative also. V min can be negative also. So these are the way when the input is changed, what happens to the output? When this resistance is not there, what happens to the output? When the resistance is there, what happens to the output? Okay, what is the voltage across diode I have got? What is the voltage across C? I should be able to find out. Voltage across diode is V out. Another question, what is the voltage across this C? How does it change? That once again remains for you to get in the various numerical questions like that. So that will be the expected your examples which you will be computing. So in terms of R and C, if I am designing, you will be able to calculate those values without any difficulty or so. Is the problem clear? What I am going to talk in clamping case? Your clamping will be changing according to the circuits that I have used. This circuit is
just like the sort of
this circuit is one. Whatever the clamping is taking place in this, what is the voltage across C? What is the voltage across RS? What is the voltage across D in this case? Here, what is the voltage across D? What is the voltage across R? Is the same as D. What is the voltage across RS? And what is the voltage across this C? So these are the things you will be expecting in the numericals. Should I go for the concept of the clamping? Students, your answer. Anything which you want here to be talked, elaborated, I can take it down. So this you already know in your basic electronics also, what a diode is behaving, what a capacitor is behaving, like that. Diode characteristic I am not taking into picture right now. Like on your variation of the diode current I am not taking. Diode current I am taking as a constant one. Only RF and RR, these two are changing, they are controlling. Only two currents are coming in. RR, reverse saturation current is coming. In case of RF, the diode current is coming. Whatever it is, voltage applied, according to that, exponentially the current will be coming over there. So that current change I am not considering in this right now. Later in some other example, I'll consider diode characteristics also. Okay? Fine. Okay, I'm taking this circuit. I'll take the sinusoidals. Here is my RS. Here is my C. Here is my diode. Simple one.
True for applications that require isolation between an and.
Now, this is my Vs. It is sinusoidal. Vs is your signal, input signal voltage. I am calling as VST. It is coming like that. This I am calling as positive. So that diode is considered forward bias. If this becomes positive, this I am taking as negative. When the polarity changes, it will be like that. Now, diode voltage is varying like this.
The ones who are working on
here it is positive, negative both. Here is my 0. Here is my V. Here is my minus V. V is the amplitude and this is my Vs. Now let me plot the output. Separately I am plotting because should not be having any problem. So what happens to the output? When the input is 0, output is 0. When the input is 0, that 0 voltage is translated to this point, output is 0. Here is my maximum. Maximum of the input. So if input is increasing, the capacitor is not charged initially, so that will be reflected at this output also. So this output will be positive, diode will be forward bias and it will be 0. So from here to here it is 0. This is my output. This I am taking as V out. V out T. So it is 0 from here to here because diode becomes forward bias. Whenever it is coming, it is forward bias, current is flowing through that. If you want to find the current, subtract the voltage drop across this RS. Okay, then you will find whether it is coming as 0 or not. Okay, so from the Vs, this current has to be subtracted. The voltage is coming at this point. Okay, so this voltage divided by Rs plus Rf is the current into Rs is the voltage drop here. So Vi minus this voltage drop is appearing across this and it is taking this to your forward bias, output will be 0. Or you can that current into Rf. This will be your current ID into Rf. Will be this voltage, either 0 or ID into Rf. That voltage will be there. What is your ID? ID is your VST by RS plus RF. Okay, if RF is 0, this becomes your 0. Like that. So it is coming like this. Up to this point, it will be forward bias. So it will be your 0 here. Okay, this is your T by 2, rather I can say. Time period by T by 4, sorry. If this is my T, time period is T, this is my T by 2. And this is my T by 4. Okay. After that, the voltage changes polarity. It is not saying it is reducing now. Now capacitor is charged to this voltage. Capacitor is charged. I am not writing it, we write it. Capacitor is charged to this voltage, that is 0 voltage. Now it is decreasing. When it was maximum, it was this. Now it is decreasing. The same thing comes at the output of the capacitor also. So that decrease will come like this. And this was my T by 2. and T by 2 it will be your V minus V. It had dropped from this voltage by V, so it is dropping to minus V. This point is your minus V. Okay, after that it is further decreasing, going down like this. So here also it will go down. It has come up to this point. And this is your 3T by 4. 3T by 4, it has gone to the maximum. And what is this? Becomes so minus 2B. I'm including RF equal to 0, that I'm analyzing. This becomes a 2B. After that, it will start increasing. Look at the input. Input is increasing, so it will also start increasing. It will come up to this point. This point will be your how much? This thing. So this point will be your 3T by 4. This becomes your T. This point will be your T. It will further increase up to this point. It will become 0 at this point. That means your T plus T by 4. Okay, so you see that whatever was there, it was coming in the same shape. It is clamped to minus V and it is shifted. Shifted by how much? If this becomes my reference, if it is clamped to this voltage, at this clamping point, the phase is shifted by T by 2, because T by 4 it started. Shifted by T by 2. Instead of T by 4, shifting to T by 4. T by 4 to T by 2. Shifting by T by 4 rather, you can say. It was 0 here, here it is T by 2. No, it is shifted by T by 2, Shifted by T by 2. Here again it is coming, it will be your T. So this is your T by 2, this is your T, and that's what. So it has been shifted by T by 2 and it clamped to this minus B. Again, here it will not be going like this 0, 0, 0 like that. Here it will be coming like this because immediately it starts falling now. Capacitor is charged, capacitor is not fully discharged. Okay, so it starts coming like that, it goes like this. So voltage is clamped. In the simple diode, voltage is clamped, input is clamped to its own amplitude in the negative direction. Okay, so it is sinusoidal signal. Now 0 has been shifted to minus B. Is it okay? So this question might come, this portion appears only for this T by 4 because initially the capacitor was considered uncharged. Here it is not uncharged. Okay, just it has just a 0 charge, and after that it will start behaving with the input signal like that. Here it started behaving after this point, because till this point diode was becoming your forward bias. Here the diode is not becoming a forward bias, just for the very small time, infinitesimal time it is becoming forward bias. After that it becomes a reverse bias and you will be getting the output according to that. So capacitor voltage appears in reverse bias, no current flows through the diode and signal appears like that. Okay, so clamping circuit in which there is no load resistance given in the design circuit. Actual load next is a different thing. There is a load given in the design circuit, that RS. Question another will be, in this case, how much is the voltage across this C? How much is the voltage across C? Whatever is coming, it is coming at this point. This is the voltage. You have to find what is the voltage drop across RS when the diode is forward bias. Diode is not becoming forward bias at all anytime. So voltage drop across RS is not there. If I consider RF, which is non-zero, some current is flowing, that voltage drop will be computed here by this VA divided by RS plus this RF. Okay, that is the current. That current into RS becomes the voltage drop here. So Vs minus that one, that voltage drop is appearing across the capacitor. It goes like this. Okay. Coming to the second circuit. Second circuit I made here. It was your resistance Rs. It was a capacitance here. There was a resistance. It can go after diode, before diode also, nothing, because it's coming as a parallel one. This is my diode. This is this. Positive negative you already know. I am finding the voltage across this diode. So this is my R, this is my C, and this is my input. VIT. Source resistance you can take as 0, design becomes simple, but if it is given, then you have to solve it. In this case, what is going to happen if it is a signal like this? This is my VI. Okay, so it is going like this. What is the output? Output is same thing. Till the diode is forward bias, output will be 0. From here to here it is 0, and this is nothing but this thing. Okay. After that it will start decreasing because diode has become reverse bias. But what is the output here? Same thing, whatever is applied here, it is coming to this point. Capacitor is not stopping that, but how much is this voltage? I said it is same thing is coming here, same thing is not coming there. What is the voltage across this? Okay, so that I have to find as, even the diode is reverse bias, the resistance R is there. So capacitor will be charging here, whatever voltage has been given, it has come over this point. Okay, so that is coming at this point, so that VI divided by RS plus R. Is the current. Okay, RS plus R will be flowing through that. So this voltage comes here. After that, your actual voltage is coming something like that. So this minus something. What is that? E to the power minus T by RS plus R into C. So this way it is decreasing. So initially it was this voltage, but voltage had decreased because capacitor is charging according to that. So it will be this voltage now. Negative voltage, so it's positive will be added there. So it is like this. So this shape will be changing. So it will be over here VI minus this thing. That will be coming over here. By putting the R, I am going to doing this. I am doing like this. So this difference is non-linear. So it will not be a sinusoidal shape, but some shape it will be getting. It will be coming like that. Okay. So if R is put, if RS is 0, T by R will be there, still it will be changing the shape. So actual voltage minus this exponential decay will be the output. Will be no, it's not that way. Vi minus this is Vi coming here also. Vi into Vi e to the power minus t. So it is your, in fact, Vi into 1 minus e to the power minus t by r dash c. That will be my V naught. So VIT, V naught T, that will be plotted. V naught is coming like this. And this clamping is done. So V naught will be Vi and so and so. What happened? It is coming at this 0. Starting from this point. Okay, so it is 0. So what will be the V naught in that case? If you reverse bias, then it will, sorry, forward bias is okay. So RS plus R, not RF, RS plus R, you are right. So that way there, in reverse bias, it will be coming like this. Forward bias, still I'm considering as 0. Okay, so any quick question? Students can ask. Any quick question is there? No question? Okay, so I think Bhushan Gupta is clamping idea I have given. Now I'll take example and I will describe what is the meaning of the clamping theorem. In fact, it's not a theorem, it's already known to them, but anyway, it has got a proof, so we call it as a theorem because it is not using any other result, so it's not a lemma, it is a theorem. So I'll talk that, and practically what happens, we are choosing RC to be very, very large. That is a practical clamping circuit. That way it will be there. So these things we'll talk on Friday class. Okay, friends, no question? Sajal Nigam? Any question? Okay.
No, sir.
Okay. Fine. So I just close it here. I'll be completing my discussion and then I will be also taking some examples and solve. If need be, I can go 5 minutes, 10 minutes extra in that. That if after 5:30 you don't have any class. So if you are taking more and more, interest in examples and all that, I will go 5-10 minutes extra in that class. Later I will start the class in time because before the quiz 2, that is the only class before to have discussion and taking examples. I'll take all kinds of examples and solve that way. RF, RR, all included, non-included, etc. Okay. So good day.